Okay, so most of what we're going to be talking about today has to do with solubility kinds of characteristics. And so we're going to kind of bridge that area between solubility and acid-base kinds of stuff that we talked about with buffers and titration curves and whatnot by talking about a third definition of acids and bases. So when we started chapter 15, we brought up this idea of kind of reviewing. We had Arrhenius theory, which was basically how we used to identify acids and bases by formula. Acids have an H, bases have an OH. It's nice and simple and easy. Unfortunately, it's not totally accurate or relevant in all cases. And so we moved on. We talked about Bronsted theory. And in Bronsted theory, you look at how does the hydrogen move? And for almost all intents and purposes, that's worked really well for us. But there's actually a third definition. The third definition is the most comprehensive definition of all. It's called Lewis theory. Lewis theory isn't following atoms at all. It's following electrons. And so we can define acidic and basic behavior based upon whether or not something is being added with a pair of electrons, or if that something is donating a pair of electrons. Now, the good news for us is that every acid and base that we've talked about to this point fits into this category as well. In fact, I've even mentioned it several times. We talked about those nitrogenous bases, those organic bases, and how they have that lone pair of electrons and they go out and grab another hydrogen to make them act as bases. That's Lewis behavior. That lone pair of electrons on that nitrogen going out and grabbing a hydrogen, that is the very definition of Lewis behavior. The only difference is we're focusing on what happens with that pair of electrons now, instead of the hydrogen that it grabbed in the first place. And what that allows us to do is we can start to see other kinds of acid-base behaviors in the absence of hydrogen ion. So the example we're giving here is the reaction of ammonia and water. And what we see in this reaction is that this lone pair of electrons inside of the ammonia on the nitrogen goes out and it grabs this hydrogen atom off of the water. Now, this hydrogen atom, because it has no need for the electrons in this bond, the electrons in this bond go back onto the oxygen, and that's how the oxygen ends up with 3 lone pairs in the form of the hydroxide ion. Now, this idea of using electrons to show, or using arrows to show electron movement, this is a familiar concept that you're going to know very, very well for those of you that end up needing to take organic chemistry. Because when it comes to drawing electronic mechanisms to show how this organic molecule gets from point A to point B, from reactant to intermediate to product, those electrons moving from one place to the next is going to be how you show that. But we're getting our first taste of it here. But what this also shows us how we can get other kinds of basic behavior when there is not hydrogen involved. So for example, again, I have ammonia. I've got this lone pair of electrons on that nitrogen atom, and they're going to go out and they're going to attack this boron and boron trifluoride. Now, why is it going to do that? Well, think about your octet rule here in the case of the boron. Boron only has 6 electrons around it from those 3 bonds to fluorine. Now, the reason it does that primarily, we talked about this at that point in chapter 4, was formal charge. Boron's formal charge is 0 when it forms only 3 bonds. But there are circumstances where this formation is advantageous to both of the molecules, even though their formal charges become non-zero in the process. We can see this behavior also taking place in substances like oxides. We've struggled with the idea of how an oxide or a sulfide or whatever could end up giving us such a basic solution. And now we have an explanation for it. We see through the formation, through the movement of the electrons on that oxygen, the creation of a basic behavior. Calcium oxide encountering sulfur dioxide, making calcium sulfite. The behaviors here are actually acid-base. They kind of fit under a wider umbrella of acid-base chemistry. And one of the places where we see this kind of application the most commonly is in the formation of complexes. Complexes are a great application of Lewis theory for acids and bases, which doesn't necessarily explain pH so much, but it does explain why the complexes form in the first place. So in this reaction, which is the Lewis acid and which is the Lewis base? Well, if we think of aluminum chloride as a covalent compound, which is not an easy concept to grapple with, considering everything we told you about what ionic looks like versus covalent. But if we think of this as a covalent compound, and it is in a lot of ways covalent, what we will see is that similar to boron, we've got an aluminum here that is electron deficient. It's lacking electrons to fill its octet. And we've got chloride ion here filled up with electrons to the max. In the process, making this tetrahedral aluminum chloride complex. Now, to get from here to here, which one of these substances is going to have to donate, give up a pair of electrons? Where's the electron pair going? It's starting in the chlorine and being added to the aluminum. And that donation of that electron pair is what forms that fourth bond. So in this schematic, here is our acid, the aluminum chloride. Here is our base, the chloride ion. And if we want to get real technical, the acid in question is the aluminum itself, because it is the aluminum ultimately that is accepting that electron pair. All right, any questions so far? So when it comes to complexes, we can talk a little bit about complexes in the sense that they are basically the formation of a series of this Lewis acid base kind of idea. Now, we do have some different names for these interactions. So, for example, that covalent bond that's being formed on the metal ion from the other thing, we call that a coordinate bond. And the thing that is attaching to the metal ion, we call that a ligand. Now, we don't got to get too deep into all of that. That's more of an inorganic chemistry kind of conversation. But basically, we can break down complexes into their metal ions and the ligands that attach to those metal ions. And the formation of these complexes can be explained through an equilibrium process given the formation constant K sub F. And I'm going to tell you, the value of K sub F is usually staggeringly large. Because for the substances that form complexes, those complexes are very, very favorable if we have enough ligand present to force that conversion to take place. And so if you remember back to when we first introduced the idea of concept of complexes, our very first lab, there were things that we had to be really careful about, especially for like the zinc. Zinc hydroxide had a very brief window where it actually existed in the solid precipitate form. Add too much ammonia, turned into the ammonia complex. Add too much hydroxide, turned into the hydroxo complex. That's because the formation values for the zinc complexes are extremely large. But the actual formation of these complexes is through a series of Lewis interactions. So let's take this one for example. This is one we're familiar with. The ammonia copper complex gives us that really dark, deep blue color that we saw in the group 2 analysis. We've seen it in other places as well. The formation constant for this tetra ammonia complex is 5 times 10 to the 13th. This complex formation is extremely favorable. So much so that if we have enough ammonia present, and that's really the key to this, if we have enough ammonia present, the concentration of uncomplexed amount of uncomplexed copper rather is going to be very, very minimal, very, very small. And that's one of the reasons why it drives up that constant so high. I mean, that's 50 trillion. We don't talk about numbers that high with equilibrium very often. We usually assume that if the number is that high, it's going to completion. And so we're going to kind of transition from that. We want to think about that in the back of our head, because as we start to talk about solubility equilibria, that complexing, that application of Lewis acid-base theory is going to be one of the ways that we can look at for as far as how do we take something that is dissolved, that is undissolved in water and make it more soluble? Are there ways to make it more soluble in water? That would be the question in front of us ultimately. So when it comes to solubility equilibria, this is the last big equilibrium variant that we are going to look at. Solubility concerns basically the amount of solute that dissolves ultimately. We usually measure that in grams per liter. And so if you look at a solubility table, that's what it's going to tell us. Solubility of sodium chloride in water is 70 grams per 100 milliliters. The solubility of lead 2 chloride in water is 1.1 times 10 to the negative 7th grams per liter, or whatever the value is. I just made that one up. Now, we're not going to deal a whole lot with grams per liter solubility. The only time you'll actually see it is if you have to convert it into molar solubility. Molar solubility is what we're going to concern ourselves with most, because our equilibrium constant is always going to be using molar concentrations. And so from that perspective, molar solubility is going to be our kind of our default mode of expressing solubility. This term here, KSP, don't get bogged down in the fact that we've got another subscript here. It's a capital K. It's an equilibrium constant. As an equilibrium constant, it is held to the same rules as every other equilibrium constant. It's products over reactants. The main difference here, this is a heterogeneous equilibrium. This solid here is a consistent feature of solubility equilibria. And since solids aren't included in the equilibrium expression, that means that we're really just dealing with a product here. And that's why it's called the solubility product constant. Because we're looking at solubility data, molar solubility. And since there's no denominator, it's just the product. And the end result is our equilibrium constant K. Now, one thing about KSP, we will always be dealing with saturated solutions. So if you remember your solution definitions from Chem 105, a saturated solution is one where we have the inability to dissolve any more stuff into it at that temperature. It's packed full. And we can only use KSP if that is the condition. If the solution is unsaturated, KSP cannot apply, because whatever concentration we have is not the full concentration. We need to keep adding until we have that true equilibrium where we've got undissolved solid and dissolved ions in that solution at the same time. Now, as far as problems are concerned, like in terms of what kinds of calculations could you be asked to do with this, they really fall into two different categories. One of the categories is determining the molar solubility S from the KSP. And the key to that problem is it's basically set up like any other ice table that you have done, only there is no denominator. You set it up, you solve for X, and this time the X, in addition to being whatever it is to help you find the equilibrium concentrations, the value of X itself is the molar solubility. Because molar solubility kinds of things, we're always going to have 1 mole of our dissolving substance. And so that's what we're ultimately trying to figure out. So even if this ends up being 2x and 2x, which this one isn't, but even if I have multiples for both of the ions, the value of X is still the molar solubility, because the molar solubility ties back to the original salt, not necessarily to any of the product ions. So KSP values usually tend to be on the smaller side. Again, we're talking about things that are not soluble in water, or at least not appreciably soluble in water. So they tend to be on the smaller side. We tend to get X values that kind of match that. One thing that we will have to notice is that we will have to be careful from time to time. Because if we have large quantities of X's, or in some cases, squares, cubes, quartics of X, that's going to lower the exponent of X considerably with each one that we do. So the more we have to divide it, the bigger our root becomes, the more of an impact it's going to have on the value. So there are going to be occasions where we have to use like 5% approximations. And if that is the case, we just got to be really careful and make sure that we've got a really big disparity between the value of the concentration and the value of K. So what are some things that can impact the solubility of our substances? Well, the first of them has been the subject of this entire chapter, the common ion effect. If I introduce another solution that shares a common ion with the solution that I'm trying to, or with the salt that I'm trying to dissolve, that is going to make that salt less soluble. So for example, if I am looking at the solubility of barium sulfate. Barium sulfate being one of those classic exceptions to the sulfate rule that we talked about in all of our solubility rules, Chem 105. If I introduce sodium sulfate, which is soluble because sodium ion is extremely soluble in water. If I introduce sodium sulfate into this solution, that is going to add to the concentration of sulfate. So the concentration is going to pick up, which is going to push that equilibrium to the left, making the solubility of barium sulfate that much lower. And so while we'll see a considerable uptick in the sulfate concentration in this scenario, what we'll find is that the barium concentration is going to vaporize. It'll still be there, but it'll be much, much lower. So once again, we see the common ion effect kind of taking hold here and giving us another shift to our equilibrium. Once again, shifting it backward toward the reactants. Another factor, pH. We can see this going in a couple of directions, actually. If I have in this example, like in this example, I've got a salt that contains a basic anion. That basic anion can react with acid at a lower pH and form its conjugate acid. So basically, we've introduced a side reaction. This side reaction happens to be the formation of a weak acid. In that scenario, the concentration of the fluoride is going to go down. So we're going to see an increase in solubility to replace the lost fluoride. Now, you know as well as I do that this equilibrium that we're talking about here is not terribly favorable toward the formation of hydrogen fluoride. It's going to be pretty good, don't get me wrong. But we do have another equilibrium at play here. So there is a limitation to it. But what we will see is that calcium fluoride, because it is basic, just in general, is going to be more soluble at lower pHs than at higher pHs. So let's take a look at a couple of examples. Our first example here. What is the expression for the solubility product constant for calcium fluoride? Well, in that one, we would be talking about calcium fluoride, the solid, in equilibrium with calcium ion and 2 fluoride ions. And we got to make sure that we are really careful about our stoichiometry here when we do these KSP expressions. We can't just assume that it breaks into 1 cation and 1 anion. We have to look at the chemical formula itself and see how many ions it breaks into. The value of KSP here would be equal to the concentration of the calcium ion multiplied by the concentration of the fluoride ion, quantity squared, because again, there are 2 fluorides there. So if you want to know the most common mistakes made in KSP expressions, is rushing through them, forgetting the exponents, doing the ice tables and forgetting that there's going to be twice as much fluoride as calcium. The little detail things that we haven't had to worry about with buffers, because buffers are always 1-to-1, we have to bring back here in KSP. And it's been a while, because Ka, Kb, 1-to-1-to-1, everything was 1. Buffers, everything was 1-to-1. So we gotta go back to our earliest concepts of equilibrium. When I'm making my ice table here, don't care about this. I'm actually going to move the ice table just to the product side. I start with nothing. I add 1x to the calcium and 2x to the fluoride because there are 2 of them. Which means that my equilibrium concentrations of calcium will be 1x, fluoride will be 2x. Using my KSP expression, 3.9 times 10 to the negative 11th is equal to x times 2x quantity squared which is x times 4x squared, which would be 4x cubed. (3.9 times 10 to the negative 11th divided by 4 is 9.8 times 10 to the negative 12th as x cubed. Take the cube root of that. (2.1 times 10 to the negative 4th molar. Now, I wrote that equals S there, not because we're being asked for it, but because we just want to reinforce that is the molar solubility of the calcium fluoride. So even though this question doesn't ask for the molar solubility, that is the molar solubility. X and S are the same thing. And so you will see in some equilibrium ice tables here, where if it's a KSP problem, instead of putting X's into the ice tables, they will put capital S's instead. Again, just to kind of hammer home that same point. X and S are the same thing. What this means for us, though, concentration of calcium is equal to 1S. So 2.1 times 10 to the negative 4th molar. Concentration of fluoride is 2S. So it'd be 4.2 times 10 to the negative 4th molar. And again, you can always check yourself, plug those two values back in to the expression, see if you get the KSP. 2.1 times 10 to the negative fourth multiplied by 4.2 times 10 to the negative fourth squared. I get 3.7 times 10 to the negative 11th. And like we've said before, with estimation, if we are close on that last sig fig, we know that we're in pretty good shape, especially when we have to round as much as we're being asked to round. 2 sig figs is not a terribly large number of digits to keep any kind of accurate measurement. All right, questions on this example? Couple more problems here. If the molar solubility of calcium fluoride at 35 Celsius is 1.24 times 10 to the negative third molar, determine KSP. So just reminding ourselves here, 1.24 times 10 negative third molar, that is our molar solubility S, which is also our value of X. So we can kind of set things up the same way that we had them in the previous problem. This much hasn't changed. We're starting with no concentration of either of the ions. We add 1x and 2x. So if we are given this value of X or S, that means that we have 1.24 times 10 to the negative third molar for the calcium, 2.48 times 10 to the negative third molar for fluoride. KSP is equal to the concentration of calcium ion multiplied by the concentration of fluoride ion squared. So 1.24 times 10 to the negative third multiplied by 2.48 times 10 to the negative third squared. Our KSP value to 3 significant figures, 7.63 times 10 to the negative 9th. And so just as a comparison, remember it was 3.9 times 10 to the negative 11th. We assume that was at 25 Celsius. We up the temperature. KSP becomes a little bit more soluble just because of the higher temperature. And that's in line with what we would expect for pretty much all solids. Increase the temperature, their solubility increases as well. In some cases, it increases enough where we can actually dissolve appreciable amounts of it, like what we see with the lead 2 chloride in our qualitative analyses. This next one's a similar kind of problem to what we saw previously. The only difference is we have not been given the molar solubility. We've been giving the mass solubility. So we'll just have to convert first. Before we get to that, we just need to set up our expression. Silver iodate in equilibrium with the silver ion and the iodate ion. its equilibrium expression is a little bit easier because it does break down into a one-to-one fashion. So the only thing that we're missing is we need to know the molar solubility. We need to know the X. For that, we're going to need to find the molar mass. So silver, 107.87, iodine, 126.9, and 3 oxygen, so 3 times 16 is 282.77. Do the math here to 3 sig figs, 1.73 times 10 to the negative 4th moles in 1 liter is 1.73 times 10 to the negative 4th molar. And that would be the molar solubility, or X. So KSP, since this is my expression, would be equal to the concentration of the silver ion times the concentration of the iodate ion, both to the first power because it is a 1-to-1 ratio. And that would be equal to 1.73 times 10 to the negative 4th quantity squared, because it's X times X. So 1.73 times 10 to the negative 4th squared. So 3 significant figures, 3.00 times 10 to the negative 8th. Now, one important secondary note that I want to make off of this. I can look at the KSP values, and based solely on the KSP values, I would come to the thought that the silver iodate was more soluble than the calcium fluoride. After all, its KSP value is smaller. Or sorry, its KSP value is larger. But we can't go off of that assumption. Unlike when we were making comparisons of Ka or Kb, where because everything was 1-to-1-to-1, we could just look at, okay, this Ka is bigger, so it's a stronger acid. This Kb is smaller, so it's a weaker base. We can't do that here. We have to actually do the math. Now, if I have 2 salts that have identical equilibria, both give a 1-to-1 ratio, both give a 1-to-2 ratio, both give a total of 5 ions, whatever the case is, yes, in that circumstance, I can compare KSPs directly. But if I don't have that as a comparison, I've got to do the math. Because what I'm going to see here is that the molar solubility of the calcium fluoride is about 10 times greater than the molar solubility of the silver iodate. The only reason the KSP is bigger is because there are more ions factoring into that KSP. So KSP alone is not enough for us to determine which one is more soluble than the other. We have to go to the solubility. We have to calculate molar solubility to get to that data. We can't just assume. All right, questions with this example? So let's come back to these factors that impact solubility. And let's take a closer look at each of them. Now, we've already mentioned the common ion effect. And we looked at something like this. I just wanted to show kind of graphically here. We can see that as our concentration of that common ion, in this case, sodium fluoride, as that concentration increases, we see that our solubility of calcium fluoride decreases considerably. And then eventually we'll start to kind of level off because we're just going to get to kind of close to 0 point. So let's take a look at that in action. What is the molar solubility of calcium fluoride at 25 Celsius in a solution that is 0.01 molar calcium nitrate? Now we're going to have to go back a couple of slides. (3.9 times 10 to the negative 11th is our KSP. The only real difference here is that in our ICE table, we're not starting with a 0 value here for the calcium. We've got 0 for the fluoride. What would be the concentration of calcium ion in 0.01 molar calcium nitrate? So this is another important exercise for us. Is to understand that when it comes to common ions, we've got to play out the concentration correctly out of the solution that is giving us the common ion. Every mole of calcium nitrate is giving us 1 mole of calcium ion and 2 of nitrate ion. So in this case, because the ratio is 1-to-1 between the calcium nitrate and the calcium ion, the concentration here is our concentration there. Just keep in mind, and this is probably more important when we start to look at substances, in particular anions that are common. If the ratio is 2 to 1, we just got to make sure that we double before we put it into the expression. In this case, it didn't matter. We get 1 calcium for every calcium nitrate. So the starting concentration is exactly the same. Now, again, they're both on the same side of the equilibrium here. So they're both going to gain. Calcium's going to gain 1x. Fluoride's going to gain 2x. It's really tempting in this scenario. It's really, really tempting to treat this like some of your other equilibrium problems and say, oh, I got a starting concentration. That one's minus x. You got to remember, they're both on the same side of the problem. So they're both going to behave the same way. They're both going to add. So when we get to the equilibrium side, it ends up being 0.010 plus x and 2x for the fluoride. So as we are solving this out, 3.9 times 10 to the negative 11th is equal to 0.010 plus x times 2x quantity squared. Now, if the concentration is high enough, which in this case it probably is, we can still use the 5% approximation and ignore that positive x term. And if we do that, 3.9 times 10 to the negative 11th divided by 0.01 divided by 4, we will get 9.75, so 9.8 times 10 to the negative 10th as x squared. If we take the square root of that, 3.1 times 10 to the negative 5th molar as x, which would be the molar solubility. So a really good check with yourself on this kind of thing would be to look at the impact of, if we ignore that positive x term, does this x value actually change the calcium concentration at equilibrium? In this case, the answer is absolutely not. That 3.1 is way over here somewhere. So it's going to round up to 0.01 anyway. If it doesn't, and it changes things considerably, turns that 0.01 to 0.01 or to 0.015, for example, that's a sign of overestimation. That's a sign that we've taken it too far and we need to go back and set up, in this case, a cubic. 0.04 x squared plus 4x cubed is equal to 3.9 times 10 to the negative 11th. Put that in to your favorite equation solver, get out your values of x. It's going to work out the same way. Even though it's a cubic and there are 3 roots, only one of them is going to make any kind of appreciable sense. The other 2 are likely to either be negative or 0 or imaginary. Imaginary is always a favorite. All right, any questions with this example using the common ion effect? All right, we've talked about this. Let's recap it a little bit. Basic solutions. So if we have a salt that we can identify qualitatively as basic, we know that that salt is going to be subject of one of 2 kinds of distortions with pH. If we add hydroxide to that basic solution, we can pretty safely assume that through the common ion effect, we're going to see a decrease in solubility. If we add hydrogen ion to that solution, we're going to see through a basically competing side reaction that the solubility will increase. So basic solutions are going to find their way in to being pH sensitive. And so the solubility at pH 7 is going to be different than the solubility at pH 10 or pH 5 or pH 2. And we can usually calculate those differences, especially if they are direct applications of common ion effect. So in particular, if I've got a hydroxide insoluble salt and I'm adding more hydroxide to it, or I'm increasing the pH of that solution through the addition of sodium hydroxide or something else, I'm going to see the solubility of that salt diminish considerably from the common ion effect. But similarly, if I lower that pH, if I introduce that hydrogen ion, it's going to react with those hydroxides. Le Chatelier's principle is going to push the reaction to the products, and we're going to get more solubility as a result. All right. Let's see how you're doing here. What is the molar solubility of magnesium hydroxide at 25 degrees Celsius? KSP for magnesium hydroxide, 5.6 times 10 to the negative 12th. Let's take a couple of minutes and work on that, and we'll come back and see how we're doing. All right, looks like most of you are on the right track, if not all of you. So this sets up very similarly to how a lot of our problems have gone thus far. We're just looking for the molar solubility here. So we've got no magnesium, no hydroxide initially. We're going to have X and 2X because of the stoichiometry being added. So the magnesium concentration be X, the hydroxide concentration be 2X. This is all going to equal out to 5.6 times 10 to the negative 12th, but we have to keep in mind it is the magnesium concentration multiplied by the hydroxide concentration quantity squared. So setting that up, 5.6 times 10 to the negative 12th is equal to x times 2x quantity squared, which is equal to x times 4x squared, which is equal to 4x cubed. Remember, x is our molar solubility. So if we solve for x, that we are solving for the molar solubility. Divide each side by 4. 5.6 times 10 to the negative 12 divided by 4 is 1.4 times 10 to the negative 12th, being x cubed. If I take the cube root of both sides, we get an x that is equal to 1.1 times 10 to the negative 4th molar. Since x is our molar solubility, that's it. We're done. All right, any questions with this problem in particular? All right, so let's do one more example, kind of in the same framework as what we were looking at with that pH common ion effect kind of idea. So we're looking at silver hydroxide. Silver hydroxide, AgOH. We need a KSP for silver hydroxide. So I'm going to have to go to my lecture packet for that. Interesting. Okay, it's not in the lecture packet. Let's consult Dr. Internet for that. All right, we're getting, according to the engineering toolbox, we're getting 2 times 10 to the negative 8th. We'll go with that. We'll add an extra sig fig just for fun. Okay, so this is a slightly different kind of problem. This is asking us for the pH of the saturated solution. Now, the reason why this is kind of different is just because this kind of marries together what we are talking about with acid-base kinds of concepts. The difference here being we're going to use this value ultimately, figure out the concentration of hydroxide, use that to figure out the POH and then the pH. So our equilibrium is going to look like this. Silver ion, hydroxide ion. Initially, we've got nothing. Our change is going to be plus X. And our equilibrium will be X and X. So as far as calculation is concerned, these are as simple as they get. The one-to-ones are easy to do because it's basically KSP, 2 times 10 to the negative 8th, is equal to concentration of silver times concentration of hydroxide, which is X times X, or X squared. So all we got to do is take the square root of the KSP, and we will get a value of X. 2 times 10 to the negative 8th, square root of that, 1.4 times 10 to the negative 4th. So that would obviously give us the molar solubility if we were being asked for the molar solubility. We aren't. We're being asked for the pH. But what we need to understand is that that X value is also the concentration of the hydroxide. So the concentration of hydroxide at 1.4 times 10 to the negative 4th, we can calculate the POH, which would be 3.85. Which would give us a pH of 10.15. So silver hydroxide on its own is giving us a pH of 10.15. Now, the question here is basically a common ion effect question. If the pH is set to 11 through the use of a buffer, sodium hydroxide, whatever the case may be, what would the molar solubility of the silver hydroxide be in that circumstance? Well, now we just have to work it around backwards. If the pH is 11, that means that the POH must be 3, and the concentration of hydroxide must be 1 times 10 to the negative 3rd. And you could work through the anti-log of this, but since the numbers here are so darn round, you don't actually need to. This concentration of hydroxide becomes our starting concentration of hydroxide in this new solubility table. So just quickly redrawing what we had above. Still have no silver, but now we've got a pretty appreciable amount of hydroxide. So X for the silver, 1.0 times 10 to the negative third plus X for the hydroxide. KSP still 2 times 10 to the negative eighth. This time it's equal to X times 1.0 times 10 to the negative third plus X. Let's try the 5% approximation, see where it takes us. So if we do that, 2 times 10 to the negative eighth divided by 1 times 10 to the negative third gives us 2 times 10 to the negative fifth. So if I took that 2 times 10 to the negative fifth and added it to the 1 times 10 to the negative third, I get 1.02 times 10 to the negative third, which would round away. So our 5% approximation was safe. We were okay. So our solubility decreased by nearly a factor of 10 here. Went from 1.4 times 10 to the negative fourth molar to 2 times 10 to the negative fifth molar. So that's not quite a factor of 10, but it's really close. And that was a relatively small pH change, to be honest. We went from just over 10 to 11. All right, any questions with this example? All right, so I'm actually going to cut the tape right here. Looking ahead for tomorrow, there isn't a whole lot left. Basically, all that is left is talking about complexes and factoring in that KF information into calculations of complex equilibria to determine whether or not a solid will dissolve, or rather better phrased, complex, or stay precipitated. And amphoterism, which is along the same lines of kind of that group of basic salts that can complex in basic solution or dissolve in acidic solution through side reaction. So those two concepts, which are not too long, and then the idea of selective precipitation, where I got this substance and this substance, and I throw in a whole bunch of fluoride. Which of the fluoride salts comes out first? That's all that's left for this chapter. And I'm going to kind of save that just because I don't want us to go too far over time, and it's going to take us over time to do so. So that is all that is left. We'll close with that tomorrow. There's a couple of examples we can do. And then that should give us some time that if you have questions, if you want to go through some things, we can do that. We can use that extra time to kind of recap and review this chapter 16, go through some extra practice problems, things that have come up in the lecture along the way. Or if we want to look ahead a little bit further, We can start taking a look at thermochemistry during that second hour and get a little bit of a jump on that information so that we can kind of lighten our load for Friday a little bit. So we'll play that off based on kind of how you're feeling about things, how many questions you have out of chapter 16. If we've got a lot of questions, we'll handle them. That's why I built in that 5th day. If we don't, no big deal. We'll just keep going along. For now, though, go ahead and hit the stoplight question, and then let's take a 5-10 minute break, get out, walk around a little bit, and we'll head over to the lab and get into the next phase of the group 3 analysis. So for most of you, that means unknown day. So let's head over there in about 5-10 minutes. And as soon as you get in there, give me, I guess it's an evaporating dish. Give me an evaporating dish. I'll give you some unknown. You can go ahead and get started right away. See you there.